Hello, and welcome to our astronomy course. I'm glad to see you again, and this is our final lecture on astronomy. Lecture number 21 is the topic life on other worlds. worlds. You know, uh, the atom of carbon, oxygen, and other heavy elements that are necessary components of you did not exist at the beginning of the universe, but were created by successive generations of stars. The elements from which you are made are common everywhere in the observable universe. So it is possible that life began on other worlds and evolved to intelligence. If so, perhaps those other civilizations will be detected from Earth. Further, future astronomers may discover distant alien species completely different from any life on Earth. Your goal in this lecture is to try to understand truly intriguing puzzles, the origin and evolution of life on Earth, and whether there is life on other worlds too. Let's start with one of the first questions today lecture, the nature of life. What is life? Philosophers have struggled with that question for thousands of years. And it is not possible to answer it in a single model. An attempt at a general definition of what living things do, distinguishing them from non-living things, might be the following. Life is a process by which an organism extracts energy from the surrounding, maintains itself, and modifies the surrounding to promote its own survival and reproduction. One very important observation is that all living things on Earth, no matter how apparently different, share certain characteristics in how they perform the process of life. The physical basis of life on Earth is the element carbon. Please look more attentively to this slide. Because of the way carbon atoms bound to each other and to other atoms, and they can join into long, complex, and stable chains that are capable, among many other feats, of storing and transmitting information. A large amount of information is necessary to control the activity and maintain the forms of living things. It is possible that life in other worlds would use silicon instead of carbon. Silicon is right below carbon in the periodic chart, which means that it shares many of carbon's chemical properties. But life based on silicon seems unlikely because silicon chains are harder to assemble and disassemble than their carbon counterparts, and so can't be as planned. Science fiction has proposed even stranger life forms based on, for example, electromagnetic fields, and ionized gas, and none of these possibilities can be ruled out. The hypothetical life forms make for fascinating speculation, but they can't be studied as systematically as life on Earth. And this lecture is concerned with the origin and evolution of life as it is on Earth, based, first of all, on carbon, not because of lack of information, but because it is the only form of life about which we know anything. Even carbon-based life has its mysteries. What makes a lump of carbon-based molecules a living thing? An important part of the answer lies in the transmission of information from one molecule to another. Most actions performed by living cells are carried out by molecules built within the cell. Cells must store recipes for making all these molecules, as well as how and when to use them, and then somehow pass the recipes on to their offspring. As for study DNA, the code of life, I noticed 3 important points and 7 new terms. And first, the chemical recipes of life are stored as a templates on DNA, deoxyribonucleic acid. DNA means, another time I repeat, deoxyribonucleic acid. This sort of molecule. DNA templates guide specific chemical reactions within the cell. Second, the instructions stored in DNA are genetic information based down to offspring. And third, the DNA molecule reproduces itself when a cell divides, so that each new cell contains a copy of the original information. To produce viable offspring, a cell must be able to make copies of its DNA. Surprisingly, it is important for the continued existence of all life that the copying process includes mistakes. Earth's environment changes continuously. To survive, species must change as their food supply, climate, or home terrain changes. If the information stored in DNA could not change, then life would go extinct quickly. The process by which life adjusts itself to changing environment is called biological evolution. When an organism reproduces, its offspring receive a copy of its DNA. Sometimes external effects like radiation alter the DNA during the parent organism's lifetime. And sometimes mistakes are made in the copying process, so that occasionally the copy is slightly different from the origin. Offspring born with random alterations to their DNA are called mutants. Most mutations make no difference, but some mutations are fatal, killing the afflicted organism before they can reproduce. In rare but vitally important cases, a mutation can actually help an organism survive. These changes produce variation among the members of a species. All of the squirrels in the park may look the same, but they carry a range of genetic variation. Some may have slightly longer tail or faster growing claws. These variations make almost no difference until the environmental changes. For example, if the environment becomes colder, a squirrel with a heavier coat or fur will, on average, survive longer and produce more offspring than its normal contemporaries. Likewise, the offspring that inherit this beneficial variation will also live longer and have more offspring of their own. These differing rates of survival and reproduction are examples of natural selection. Over time, the beneficial variation increases in frequency, and the species can evolve until the entire population shares the trait. In this way, natural selection adopts species to their changing environment by selecting from the huge array of random variation, though that would most benefit the survival of the species. It is a common misconception that evolution is random, but that is not true. The underlying variation within species is random, but natural selection is not random because progressive changes in a species are directed by changes in the environment. Let's analyze the next scientific argument. Why it is important that errors occur in coding DNA. Sometimes the most viable scientific arguments are those that challenge what seems like common sense. It seems obvious that mistakes shouldn't be made in copying DNA, but in fact, variation is necessary for long-term survival of a species. For example, the DNA in a starfish contains all the information the starfish needs to grow, develop, survive, and reproduce. The information must be passed on the starfish offspring for them to survive. But that information must change if the environment changes too. A change in the ocean's temperature may kill the specific shellfish that the starfish eats. If none of the starfish are able to digest another kind of food, if all the starfish have exactly the same DNA, they will all die. But if a few starfish are born with the ability to make enzymes that can digest a different kind of shellfish, the species may be able to carry on. Variations in DNA are caused both by external factors, such as radiation, and by occasional mistakes in the copying process. The survival of life depends on this delicate balance between mostly reliable reproduction and the introduction of small variations in DNA. Now, build a new argument. How does DNA make copies of itself? How do you think? And now it's time to start another topic today's lecture, the origin of life. It is obvious that the 4.5 billion chemical bases that make up human DNA did not just come together in the right order by chance. The key to understanding the origin of life lies in the process of evolution. The complex interplay of environmental factors with the DNA of generation after generation of organisms drove some life forms to become more sophisticated over time until they became the unique and specialized creatures on Earth today. This means that life on Earth could have begun very simply, even as simple as carbon chain molecules able to copy themselves. Of course, this is a hypothesis for which you can seek evidence. What evidence exists regarding the origin of life on Earth? The oldest fossil are remains of sea creatures, and this indicates that life began in the sea. Identifying the oldest fossils is not easy, however. Rocks from Western Australia that are at least 3.4 billion years old contain features that biologists identify as stromatolites. Fossils remains of colonies of single-celled organisms, as you can see on this slide. Fossils, these old, are difficult to recognize because the earliest living thing did not contain easily preserved hard parts like bones or shells, and because the individual organisms were microscopic. The evidence that cars indicates that simple organisms lived in Earth's oceans at least 3.4 billion years ago, less than 1.2 billion years after the Earth's form. Stromatolite colonies of microorganisms are more complex than individual cells, so you can imagine were probably earlier, simpler organisms. Where did those first simplest organisms come from? An important experiment performed by Stanley Miller and Harold Urey in 1952 sought to recreate the conditions in which life on Earth began. The Miller experiment consisted of a sterile sealed glass container holding water, hydrogen, ammonia, and methane. An electric arc inside the apparatus creates sparks to simulate the effects of lightning in Earth's early atmosphere. As you can see, experiment on the left part on figure A in this slide. Miller and Urey let the experiment run for a week and then analyzed the material inside. They found that the interaction between the electric arc and the simulated atmosphere had produced many organic molecules from the raw material of the experiment, including such important building blocks of life as amino acids. When the experiment was run again using different energy sources, such as hot silica to represent molten lava spilling into the ocean, similar molecules were produced. Even a source of ultraviolet radiation, representing the small amount of ultraviolet in sunlight, was sufficient to produce complex organic molecules. Scientists are professionally skeptical about scientific findings, and they re-evaluated the Miller-Urey experiment in light of new information. According to updated models of the formation of the solar system and Earth's early atmosphere probably consisted mostly of carbon dioxide, nitrogen, and water vapor instead of the mix of hydrogen, ammonia, methane, and water vapor assumed by Miller and Urey. Okay? When gases corresponding to the newer understanding of the early Earth's atmosphere and processed in a Miller apparatus, lesser but still significant numbers of organic molecules are created. The Miller experiment is important because it shows that complex organic molecules form naturally in a wide variety of circumstances. Lightning, sunlight, and hot lava are just some of the energy sources that can naturally rearrange simple common molecules into the complex molecules that make life possible. If you could travel back in time, you would expect to find Earth's first ocean filled with a rich mixture of organic compounds called the primordial soup. Many of these organic compounds would have been able to link up to form a larger molecule. Amino acids, for example, can link together to form proteins by joining ends and releasing a water molecule, as you can see on this slide. That reaction, however, does not proceed easily in a water solution. Scientists hypothesize that this step may have been more likely to happen in some warm tidal pool or on shorelines where organic molecules from the primordial soup could have been concentrated by evaporation. The production of large organic molecules may have been aided in such semi-dry environmental by clay crystals acting as templates to hold the organic subunits close together. These complex organic molecules were still not living things, even though some proteins may have contained hundreds of amino acids. They did not reproduce, but rather linked and broke apart at random. Because some molecules are more stable than others, and some bound together more easily than others. Scientists hypothesize that a process of chemical evolution eventually concentrated the variation smaller molecules into the more stable larger form. Eventually, according to the hypothesis, somewhere in the oceans, after sufficient time, a molecule formed that could copy itself. At that point, the chemical evolution of molecules became the biological evolution of living things. An alternate theory for the origin of life holds that reproducing molecules may have arrived here from space. Radio astronomers have found a wide variety of organic molecules in the interstellar medium, and similar compounds have been found inside meteorites. Let's look to this side, please. The Miller experiment showed how easy it is to create complex organic molecules from simple compounds. So it is not surprising to find them in space. Although speculation is fun, the hypothesis that life arrived on Earth from space is presently more difficult to test than the hypothesis that life on Earth originated on Earth. Whether the first reproducing molecules formed here on Earth or in space, the important thing is that they could have formed by natural processes. Scientists know enough about those processes to feel confident about them. even though some of the steps remain unknown. The details of the evolution of the first cells are unknown, but the first reproducing molecule to surround itself with a protective membrane would have gained an important survival advantage. Experiments have shown that microscopic spheres the size of cells containing organic molecules form relatively easily in water, as you can see in this slide. So, the evolution of cell membranes is not surprising. The first cell must have been simple, single-celled organisms, much like modern bacteria. As you learned earlier, these kinds of cells are preserved in stromatolites. This is a mineral formation produced by layers of photosynthetic bacteria and shallow ocean sediment. Stromatolites are in rocks with radioactive ages 3.4 billion years, and they also still form in some places today. Stromatolites and other photosynthetic organisms would have begun adding oxygen, a product of photosynthesis, to Earth's early atmosphere. Let's look to this figure, please. An oxygen abundance of only 0.1% would have created an ozone screen, protecting organisms from the sun's ultraviolet radiation, and later allowing life to colonize the land. Over the course of eons, the natural processes of evolution gave rise to stunningly complex multicellular life forms with their own widely differing ways of life. It is a common misconception to imagine that life is too complex to have evolved from such simple beginnings. It is possible because small variations can accumulate. Also, that accumulation requires huge amounts of time. Life has existed on Earth for at least 3.4 billion years. But there is little evidence of anything more than simple organisms until about 540 million years ago, when life suddenly branched into a wide variety of complex forms like the trilobites. Let's look to this figure, please. This sudden increase in complexity is known as the Cambrian explosion and marks the beginning of the Cambrian period. If you represented the entire history of Earth on a scale diagram, the Cambrian explosion would be near the top of the column, as shown at the left part of this figure. The emergence of most animals familiar to you today, including fishes, amphibians, reptiles, birds, and mammals, would be crammed into the topmost part of the chart, above the Cambrian explosion. If you magnify the proportion of the diagram, as shown on the right side of this figure, you can get a better idea of when these events occurred in the history of life. Humanoid creatures have walked on Earth for about 4 million years. This is a long time by the standard of a human life, but it makes only a narrow red line at the top of the diagram. Look at this age of human on the top. All of recorded history would be a microscopically thin line at the very top of the column. So look at this another time. To understand just how thin that line is, Imagine that the entire 4.6 billion year history of the Earth has been compressed onto a year-long video, and that you began watching this video on January 1. You would not see any signs of the life until March or early April. And the slow evolution of the first simple form would take the next 6 or 7 months. Suddenly, in the mid-November, you would see the trilobites and other complex organisms of the Cambrian explosion. You would see no life on any kind of land until November 28. But once life appeared, it would diversify quickly. And by December 12, you would see dinosaurs walking the continent. By the day after Christmas, they would be cool, and mammals and birds would be on rise. By imagining the history of Earth as a year-long video, you have gained some perspective on the rise of life. Tremendous amount of time were needed for the first simple living thing to evolve in the ocean. But as life became more complex, new forms arose more and more quickly as the hardest problem: how to reproduce, how to take energy efficiently from the environment, how to move around, were solved by the process of the biological evolution. The easier problems, like what to eat, where to live, and how to raise young, were managed in different ways by different organisms, leading to the diversity that is seen today. Even intelligence, that which appears to set humans apart from the other animals, may be a unique solution to an evolutionary problem posed to humanity's ancient ancestors. A smart animal is better able to escape predators, outwit its prey, and feed and shelter itself and its offspring. So, under certain conditions, evolution is likely to select for intelligence. Could intelligent life arise on other worlds? To try to answer this question, you can estimate the chances of any type of life arising on other worlds. Then assess the likelihood of world life developing intelligence. Our next topic is life in our solar system. Could there be carbon-based life elsewhere in our solar system? Liquid water seems to be a requirement of a carbon-based life, necessary both as the medium for the vital chemical reactions and to transport nutrients and waste. It is not surprising that life developed on Earth's oceans and stayed there for billions of years before it was able to colonize the land. Scientists are in agreement that any world harboring living thing must have significant quantities of some type of liquid. Water is a cosmically abundant substance with properties such as high heat capacity that set it apart from other common molecules that are liquid at the temperatures of planetary surfaces. Maybe there are other liquids that can support the processes of life on other planets. But water, aside from being common in the universe, has characteristics that cause those scientists to regard it as a special, and not just because they are made of water themselves. Many worlds in the solar system can be eliminated immediately as cause for life, because liquid water is not possible there. The moon and Mercury are airless, and water would boil away into space immediately. Venus has traces of water vapor in its atmosphere, but it is too hot for liquid water to survive on the surface. The Jovian planets have deep atmosphere, and at a certain level, it is likely that water condenses into liquid droplets. However, it seems unlikely that life could have originated there. The Jovian planets do not have solid surfaces, so isolated water droplets cannot mingle to mimic the rich primordial oceans of Earth, where organic molecules grew and interacted. Additionally, powerful downdraft currents in the gas giant's atmospheres would quickly carry and reproducing molecules that did form there into inhospitality for regions of atmosphere. As you learned earlier, at least one of the Jovian satellites could potentially support life. Jupiter's moon Europa appears to have a liquid water ocean below its icy crust, and mineral dissolved in the water could provide a rich source of raw material for chemical evolution. Europa's ocean is kept warm and liquid now by tidal heating. There also may be liquid water layers under the surfaces of Ganymede and Callisto that can change as the orbit of the moons interact. Europa, Ganymede, and Callisto may have been frozen solid at other times in their history. Saturn's moon Titan is rich in organic molecules. Lecture about Jovian planets described how sunlight converts the methane in Titan's atmosphere into organic smoke particles that settle to the surface. The chemistry of life that could have evolved from those molecules and survived in Titan's likes of methane is unknown. It is fascinating to consider possibilities, but Titan's extremely low temperature of minus 180 centigrade and would make chemical reactions slow to the point where life processes seem unlikely. Water-containing organic molecules has been observed venting from the south polar region of Saturn, Moon, and Enceladus. It is possible that life could exist in that water under Enceladus crust, but the Moon is very small, and its tidal heating might operate only occasionally. Enceladus may not have had plentiful liquid water for the extended time necessary for the rise of life. Mars is the most likely place for life to exist in the solar system because, as you learned earlier, there is a great deal of evidence that liquid water once flowed on its surface. Even though results from researchers from foreseeing signs of life on Mars are not encouraging. The robot spacecraft Viking 1, Viking 2, and many moderns now landing on Mars from 1976 and tested soil samples are living organisms. Some of the tests had puzzling semi-positive results that scientists hypothesized were caused by non-biological chemical reactions in the soil. No evidence clearly indicates the presence of life or even organic molecules in the Martian soil. There was a splash of news stories in the 1990s regarding some supposed chemical and physical traces of life on Mars discovered inside a Martian meteorite found in Antarctica. Scientists were excited by the announcement, but they employed professional skepticism and immediately began testing the evidence. The results suggest that the unusual chemical signatures in the rock may have formed by processes that did not involve life. Tiny features in the rock that were originally thought to be fossils of the ancient Martian microorganisms could possibly be non-biological minerals for formations instead. This is the only direct evidence yet found regarding potential life on Mars, but it remains highly controversial. Conclusive evidence of life on Mars may have to wait until a geologist from Earth can scramble down dry Martian streambed and crack open rocks looking for fossils. There is no strong evidence for the existence of life elsewhere in the solar system. Now your search will take you to distant planetary systems. Could life exist in other planetary systems? You already know that there are many different kinds of stars, and that many of these stars have planetary systems. As a first step toward answering this question, you can try to identify the kinds of stars that seem most likely to have stable planetary systems where life would evolve. If a planet is to be a suitable home for living things, it must be in a stable orbit around its sun. Okay? That is easy in a planetary system like ours. But planet orbits in binary star systems would be unstable unless the component stars are very close together or very far apart. Astronomers can calculate that in binary systems with stars separated by intermediate distance of a few astronomical units, the planets should eventually be swallowed up by one of the stars or ejected from the system. Half the stars in the galaxy are members of binary systems, and many of them are unlikely to support life on planets. Moreover, just because a star is single does not necessarily make it a good candidate for sustaining life. Earth required perhaps as much as 1 billion years to produce the first cell and 4.6 billion years for intelligence to emerge. Massive stars that live only a few million years do not meet these criteria. Are you agree with me? If the history of life on Earth is representative, then stars more massive and luminous than about special type F5 are too short-lived for complex life to develop. Main sequence stars of type G and K, and possibly some of the faint M stars, are the best candidates. The temperature of planet is also important, and that depends on the type of star, its orbits, and its distance from the star. Astronomers have defined a habitable zone around a star as a region within which planets have temperatures that permit the existence of liquid water. The Sun's habitable zone extends from around the orbit of Venus to the orbit of Mars, with Earth right in the middle. A low luminosity star has a small habitable zone, and a high luminosity star has a large one. Scientists on Earth are finding life in places previously judged inhospitable, such as the bottom of ice-covered lakes in Antarctica and far underground inside solid rock. Life has also been found in boiling hot springs with highly acidic water. As a result, it is difficult to pin down a range of environments and be sure that life cannot exist outside those conditions. You should also note that three of the environments listed as possible heavens for life, Europa, Titan, and Enceladus, are in the outer solar system, far outside the Sun's conventionally defined habitable zone. Stable planets inside the habitable zones of long-lived stars are the places where life seems most likely, but given the tenacity and resilience of Earth's life force, there might be other seemingly inhospitable places in the universe where life exists. Now, let's start scientific argument. What evidence indicates that life is possible on other worlds? A good scientific argument involves careful analysis of evidence. Fossils on Earth show that life organized in the oceans at least 3.4 billion years ago. And biologists have proposed likely chemical processes that could have eventually yielded reproducing molecules inside membranes. The first simple life form. Fossils show that life development slowly at first. The pace of evolution quickened about 500 million years ago, when life took on complex form. Later, when life emerged onto the land, it evolved rapidly into the diverse form. Intelligence is a relatively recent development. It is only a few million years old. If this evolutionary process occurred on Earth, it seems reasonable that it could have occurred on the other worlds as well. Earth-like worlds could be plentiful in the universe. Life may begin and eventually evolve to intelligence on any other world where conditions are right. Now make a related argument. What are the conditions you should expect on other worlds that host life? And we turn to another subtopic today's lecture: communication with distant civilization. Visiting extrasolar planets is, for now, generally speaking, impossible. But nevertheless, if other civilizations exist, it is possible humans can communicate with them. Nature puts restrictions on the pace of such conversation. But the main problem lies in the unknown life expectancy of civilization. The distances between stars are almost beyond comprehension. The space shuttle would take about 150,000 years to reach the nearest star. The obvious way to overcome this huge distance is with tremendously fast spaceships. But even the closest stars are many light years away. Nothing can exceed the speed of light, and accelerating a spaceship close to the speed of light takes huge amounts of energy. Even if you travel more slowly, your rocket will still require massive amount of fuel. If you were piloting a spaceship with the mass of a yacht to the nearest star, 4 light years away, and you wanted to travel at half the speed of light, so as to arrive in 8 years, the trip would require 400 times as much energy as the entire United States consumes in 1 year. These limitations not only make it difficult for humans to leave the solar system, but they would also make it difficult for aliens to visit Earth. Reputable scientists have studied unidentified flying objects, UFO, and have never found any evidence that Earth is being visited or has ever been visited by aliens. Humans are unlikely ever to meet aliens face to face. However, communication by radio across interstellar distances takes relatively little energy. Nature puts restrictions on travel through space, and it also restricts astronomers' ability to communicate with distant civilization by radio. One restriction is based on simple physics. Radio signals are electromagnetic waves and travel at the speed of light. Due to the distances between the stars, the speed of radio waves would severely limit astronomers' ability to carry on normal conversation with distant civilization. Decades could elapse between asking a question and getting an answer. So rather than try to begin a conversation, one group of astronomers decided in 1974 to broadcast a message of greeting towards the globular cluster M13, 26,000 light years away, using the Arecibo radio telescope. When the signal arrives at 26,000 years in the future, alien astronomers may be able to understand it because the message is anti-coded, meaning that it is intended to be decoded by beings about whom we know nothing except that they built a radio telescope. The message is a string of 1,679 pulses and gaps. Pulses represent 1 second and gaps represent 0 second. Zeros. No second. Pulses represent 1 and gaps represent 0. The string can be arranged in only 2 possible ways: as 23 rows of 73 or 73 rows of 23. The second arrangement forms a picture containing information about life on Earth, as you can see on this slide. Also, the 1974 Arecibo beacon was the only powerful signal sent purposely from Earth to other solar systems. Earth is sending out many other signals. Shortwave radio signals, such as TV and FM, have been leaking into the space for at least 50 years or so. Any civilization within 50 light years could already have detected Earth's civilization. That works both ways. alien signals, whether intentional messages of friendship or the blizzard of their evidence equivalent to daytime TV, and could be arriving at Earth now. Astronomers all over the world are pointing radio telescopes at the most likely star and listening for alien civilization. Which channels should astronomers monitor? Wavelengths longer than 30 centimeters would get lost in the background noise of the Milky Way galaxy, while wavelengths shorter than about 1 centimeter are mostly absorbed in Earth's atmosphere. Between those wavelengths is a radio window that is open for communication. Even this restricted window contains millions of possible radio frequency bands and is too wide to monitor easily. But astronomers may have thought of a way to narrow the search. Within this window lie the 21 centimeter spectral line of neutral hydrogen and the 18 centimeter line of OOH, as you can see on this figure. The interval between those lines has low background interference and is named the water cone because H plus OH yields water, right? Any civilization sophisticated enough to do radio astronomy research and must know of these lines and might appreciate their significance in the same way as do Earthlings. A number of searches for extraterrestrial radio signals have been made, and some are now underway. This field of study is known as SETI, Search for Extraterrestrial Intelligence, and it has generated heated debate among astronomers, philosophers, theologians, and politicians. Congress funded a NASA search for a short time, but ended support in the early 1990s because it feared public reaction. In fact, the annual cost of a major search is only about as much as a single Air Force attack helicopter. But much of the reluctance to fund searches probably stem from issued others and costs. One point to keep in mind is that the discovery of real alien intelligence would cause a huge change in humans' worldview, akin to Galileo's discovery that the moons of the Jupiter do not go around the Earth. Some turmoil would likely result. In spite of the controversy, the search continues. The NASA SETI project, canceled by Congress, was renamed Project Phoenix and completed using private funds. The SETI Institute, founded in 1984, managed Project Phoenix plus several other important searches, and it's currently building a new radio telescope array in Northern California, collaborating with the University of California, Berkeley, and partially funded by Paul Allen of Microsoft. There is even a way for you to help with searches. The Berkeley SETI team, no, by the way, they are separate from the SETI Institute, with the support of the Planetary Society, and has recruited about 4 million owners of personal computers that are connected to the internet. The search continues, but radio astronomers struggle to hear anything against the worsening bubble of radio noise from human civilization. Wider and wider sections of the electromagnetic spectrum have been used for earthly communication. And this, combined with stray electromagnetic radiation from electronic devices, including everything from computers to refrigerators, makes hearing faint radio signals difficult. It would be ironic if humans fail to detect faint signals from another world, because our own world has become too noisy. Ultimately, the chance of success depends on the number of inhabited worlds in the galaxy. Given enough time, the searchers will find other worlds with civilization, assuming that there are at least a few out of there. If intelligence is common, scientists should find signals relatively soon, within the next few decades. But if intelligence is rare, it may take much longer. Simple arithmetic can give you an estimate of the number of technological civilizations in the Milky Way galaxy with which you might communicate and stop still. The formula proposed by discussions about n is named the Drake equation after the radio astronomer Frank Drake, a pioneer in the search for extraterrestrial intelligence. The version of the Drake equation presented here is modified slightly from its original form. And the first component will be n instead of r. The star is the number of stars in our galaxy. And Fp, it represents the fraction of stars that have a planet. If all single stars have planets, Fp is about 0.5. The factor NHC is the average number of planets in each planetary system suitably located in the habitable zone, meaning, for the sake of the present discussion, the number of planets per planetary system possessing little liquid water. Europa and Enceladus in our solar system show that liquid water can exist due to the tidal heating outside the conventional habitable zone that in our system contains Earth's orbit, and thus N sub Hc may be larger than had been originally thought. The factor F sub L is a fraction of suitable planets on which life begins. And F sub I, next component, is a fraction of those planets where life evolves to intelligence. The 6 factors on the right-hand side of the Drake equation can be roughly estimated, with decreasing certainly as you proceed from left to the right. The final factor is extremely uncertain. That factor F sub S is the fraction of a star's life during which an intelligent species is communicating. If a society survives at a technological level for only 100 years, the chances of communicating with it are small. On the other hand, a society that stabilizes and remains technological for a long time is much more likely to be detected. For a star with a lifespan of 10 billion years, F sub S might conceivably range from 10 in power minus 8 for extremely short-lived society to 10 in power minus 4 for societies that survive for 1,000,000 years. So this table summarizes what many scientists consider a reasonable range of value for F sub S and other factors. If the optimistic estimates are true, there could be a communicative civilization within a few tens of light years from Earth. On the other hand, if the pessimistic estimates are true, Earth may be the only planet that is capable of communication within thousands of the nearest galaxy. Let's come to scientific argument. Why does the numbers of civilizations that could be detected depend on how long civilizations survive at a technological level? This scientific argument depends on timing of events. If you turned a radio telescope to the sky and scanned millions of frequency bands for many stars, you would be taking a snapshot of the universe at a particular time. Broadcasts from other civilizations must be arriving at the same time if they are to be detected. If most civilizations survive for a long time, there is a much greater chance that you will detect one of them in your snapshot than if civilizations tend to disappear quickly due to nuclear war or environmental collapse. If most civilizations last only a short time, there may be none capable of the transmitting during the short interval when Earth's lights are capable of building radio telescopes to listen for them. The speed at which astronomers can search for signals is limited because computers must search many frequency intervals, but not all frequencies inside those radio windows are subject to intensive search. Build a new argument to explain why does the water hold an especially good frequency band in which to listen. How do you think? You might be resolve this in the future. And now, congratulations. This is over for your 2-semester astronomy course. And this is your great leap. Congratulations. And I hope it will be only one of your first steps to your future astronautics. I hope you enjoyed this course, and I'm looking forward to seeing you next semester to join to new very interesting 3-semester course physics. After that, it will be astro. And now, bye. See you on the nearest future.